And we discussed how the power spectrum emerges in this linear theory, and this is the primordial part. This is a part that is processed due to the radiation-dominated epoch of the universe, and there is supposed to be a peak here, and then there's a different way of showing the same thing in a dimensionless manner. And then we also discussed what this cutoff might be due to particle physics-wise, and about observationally trying to constrain models of dark matter or topology by looking at the power spectrum in observation. So all of this is in the linear regime. But as we discussed earlier in the first slide that I showed you in yesterday's lecture, the simulation movie, that the density contrast that one is talking about, although it is small compared to one in the early phases of the evolution of the universe, at late times, once structures start to develop, the density contrast becomes very large, can become of order hundreds or of order 0.1 or minus 0.1, something. So these are numbers that are comparable to unity, and then you cannot do perturbation theory. So then you enter what is called the nonlinear regime, and you need approximate techniques. Okay, so the classic approximation for all physicists is the spherical cow, and here the spherical cow is being used to describe the growth of structure in a simplified version of the problem that we have looked at. So this simplified version of the problem is written down here. Okay, so what you say is that my initial density contrast, my initial density field, let us assume that there is a center in the universe, and this initial density field is higher than average in a spherical region around this center. Okay, so I pick a point and I say that the initial density field is some value, it's a constant value around this center. So I'm plotting rho as a function of r initially. And out to some radius r, it is some constant value, and then it drops and it becomes some other smaller constant value. And this smaller constant value extends all the way out to infinity. So this is a slight variation on the homogeneous and isotropic universe. In the homogeneous and isotropic universe, the density field from any point, if you start measuring the density field outwards, you would get the same number, correct? Because the universe is homogeneous. So it doesn't matter where I sit. I sit there and I put spheres around me and I ask what is the density field at the surface of every sphere. It will be the same value everywhere. It's a constant value. It's the cosmic density. So this model is a slight variation. It says that you think of a spherical region which you have carved out, and in that carved out region, I put in a higher density. I put in more mass than there should be in a homogeneous universe. And now I ask the question, how does this density field evolve as a function of time? Okay? And I can do this in that dynamical setup that we had discussed with the Poisson equation, the Euler equation, the continuity equation, etc. But a nice thing happens, because when you do all that, you realize that actually the only thing you need to worry about is this boundary, the location of this boundary. Okay, and once you know how the location of the boundary changes as a function of time, you can solve this entire problem analytically. Okay, so you can take that system of equations, Euler continuity and Poisson equations, and you can convert it into a single differential equation for the location of this boundary as a function of time. Okay, and that equation is given here. Has anybody seen this equation before? No. This equation. Huh? No, this is just the name I have given. Have you seen this equation before? I mean, what is this right hand side? What does it remind you? What is it called? There's a famous person, Newton's law. So this is Newton's law. Okay, so that entire system of equations reduces to Newton's law for the location of this outermost boundary. And here, this quantity m less than r comma t is the mass enclosed inside the boundary at time t, and r, capital R, is the radius of the boundary at time t. So at any time t, I need to know what is the radius of this outermost boundary and how much mass is contained. in this particular simplified setup with these initial conditions, this mass actually is a constant. It is simply determined by the initial conditions themselves. Okay, so here, if I, in the initial conditions, if I ask how much mass there is, then that mass will always remain the same. You can prove this also. The Euler equation will tell you. Okay, so that's why this equation becomes very simple, that this mass becomes a constant. So I literally have Newton's law. I have d2r by dt squared is proportional to minus 1 by r squared. I have to solve this. When was the first time that you came across this equation and solved it? So far back that you don't even remember. I remember solving it in 12th standard. Okay, projectile motion, in the presence of gravity, you take a stone and you throw it upwards. And you ask what is the trajectory of this stone. It is governed by this equation. And in fact, the initial conditions of that problem, where you take a stone and you throw it upwards, is identical to what you will use here. Because here you want to say that my initial conditions, what are they? They are the conditions of the universe at some very early time. I want to think of this initial density enhancement as a small enhancement compared to the average, because that's consistent with my CMB, right? So in such a situation, all I'm saying is that my universe is almost perfectly homogeneous and isotropic with a small density enhancement. So if it is almost perfectly homogeneous and isotropic, and I'm sitting at the center for an exactly homogeneous and isotropic universe, from that point of view of the center, the velocity of this shell would be radially outwards. This is called Hubble's flow, right? Hubble law. So here also, I will set initial conditions which are an outward flow. But an outward flow is not very different from standing on the surface of the earth and throwing a stone upwards. Because relative to the center of the earth, I am defining an initially outward flow. And then there is a mass contained inside the sphere, which is a constant. The earth's mass is a constant. And I'm just saying, starting with an initially outward velocity with a constant mass, what is the trajectory of the particle, right? I'm doing exactly the same calculation here. So I don't have to discuss further. I just open my 12th standard notebook and I see what was the solution. Okay, and the solution was this. That I can parameterize this solution in terms of an auxiliary angle-like variable. It's not a real angle. It's an auxiliary variable, theta. And I will get a solution which looks like T proportional to theta minus sine theta, R proportional to 1 minus cos theta. And if I plot it, it looks like this. Right? So imagine this is the height of the stone as a function of time. What will happen to the height of the stone if I give it an initial kick? It will go up, it will reach a maximum value, it will come back down. Okay, perfectly symmetric in time. That is exactly what this is doing. It's called a cycloid solution. Right? So the cycloid is my analytical solution. I didn't have to do anything, right? I just talk, and in a few minutes you realize that this is a analytical solution to a almost realistic problem. Okay, so this is the power of approximations. Of course, it is not realistic because you will say that this kind of density field means that there is a central observer, and we know that there is no special place, etc. It is fine. This is just an approximation. Because now I can imagine saying that, imagine there are many such regions. They are very far away from each other, but everywhere locally there is a density enhancement. And maybe in some regions there is a density decrement. Okay, so instead of a positive enhancement, I can also give a negative enhancement. And I can ask how that evolves, and I can solve that also. Okay, so this is a reasonably realistic description of a localized overdensity. And you have simplified the problem immensely by introducing symmetry. So this symmetry is very powerful. It took three nonlinear coupled partial differential equations, Euler, Poisson, and continuity, converted it into a single ordinary differential equation. It is still nonlinear, but it is a very simple ordinary differential equation, which we know how to solve. Okay.
The radius of the sphere is fixed.
So this is the radius of the sphere, no? So it is changing with time, right? So this is what I have plotted here. The radius of the sphere changes with time. What you can now ask is, if the radius of the sphere is changing with time and the mass inside we argued is a constant, then what will happen to the density? Will it remain constant? It will change with time. Okay, so just looking at the radius, since the mass is constant, just staring at the radius, you should be able to figure out qualitatively how the density will change. Right? So starting from some initial value, the density will initially what? Increase or decrease? Decrease, because the radius is increasing. Then it will reach some minimum value at the time when the radius has reached its maximum value. And then look what happens. After that, the radius just keeps falling and it reaches zero at some point. So now, because the mass is the same, the density is actually growing to such an extent that it even becomes infinite in this simple model, right? And you can write down analytically what the evolution of the density is. It is given here. I just took that mass divided by r cube. Okay. And I have non-dimensionalized the problem by dividing by rho bar. This is what we call 1 plus delta. But what is rho bar here? Rho bar is the evolution of the mean density of the universe. We are assuming a universe in which, for this particular case, a universe in which there is no cosmological constant. So there is only non-relativistic matter. So it's an omega matter equal to 1 universe. No radiation, no cosmological constant, no curvature. Okay? You can calculate the evolution of the scale factor in this universe. It gives you a proportional to t to the 2/3. So once I know the scale factor, I can calculate h squared, because h squared is like 1 over a cube. So h squared behaves like what? 1 over a cube, and a cube itself is t to the 2/3. So h squared behaves like 1 over t squared. Yeah? So this rho bar, which is h squared, behaves like 1 over t squared. So that is why this theta minus sine theta squared is appearing, because t is theta minus sine. Okay, so this is a 1 over t squared from rho bar which came on top. And this 1 minus cos theta cube is just r cube, because you have taken rho, which is 1 over r, right? Mass by volume. So this is very easy to understand, and the 9 by 2 comes out when you put in the constants of proportionality property. Okay. So now you can do various things with this. This by itself is nice. Why? Because it allows you to go from an initial condition, which is a tiny perturbation. Imagine this is just 1 part in 10 to the 5 or something. So it is, if this is at 1, this is 1.00001. This is the initial condition. But in the final state, the density is going to become very, very large. Right? Because as I make my radius smaller and smaller after the turnaround, my density is going to increase. So my density is not always going to be a small perturbation around the mean density. It can become very large. And this is very nice, because this is the kind of situation I want to be. Now there is a problem here that when you send t to this value or whatever, as theta progresses, t also progresses. And then at some finite time in the future, r becomes 0 in this model. This is not nice, because if you really take this seriously, then you have formed a black hole or something that's become smaller than a Schwarzschild radius, will become a black hole. This is not what you want. So you have to put in a little bit of hand waving now and say that how long will you trust this model? Okay, how far into the future will you trust this evolution? And here you invoke the idea of virialization. So virialization is an equilibrium that forms because of random motions. And the virial theorem you might have come across, when you say that if I have a system in which I have many, many particles which are on different orbits, right? And there is a typical frequency of each of those orbits, a typical time period of all of those orbits. Maybe there's a maximum time period for any given orbit. And I now say that these orbits are randomly aligned with respect to each other, and they have random amounts of angular momentum and so on. And this is my system, and it has reached some kinetic equilibrium. So in such a situation, if I wait for an amount of time which is much longer than any of the time periods of the orbits, then many, many orbits would have passed for any given particle which is sitting here. When I wait for a very long amount of time, I have averaged over many, many such orbits. Okay. So if I calculate the inertia tensor of this system and I take its time derivative, in an average sense, this time derivative will vanish over a long period, because I have many, many orbits, I'm just averaging. And this allows you to derive the so-called virial theorem, which simply says that for this system, 2 times the kinetic energy of the velocities plus the total potential energy due to gravity is equal to 0. Okay? So this we understand from realistic systems which have random motions in it. In this system, we did not put any random motions. We just said there is a spherical overdensity, it is going out, it is coming back in. So now we have to do the following hand waving. We have to say that, okay, it goes out, it comes back in. But as it is coming back in, we have to imagine that the realistic version of this unrealistic system has random motion. Okay. So we will follow the trajectory of this unrealistic system up to a point where the realistic system would have obeyed the Viral theorem. You can ask this question. So you can say, when will the Viral theorem be satisfied by this unrealistic system? Okay. So in order to do that, I have to calculate the kinetic energy. And in this unrealistic system, there are no random motions. So kinetic energy is just given by the rate of change. So the velocity is just the rate of change of that spherical radius outwards. So dr by dt. So my kinetic energy is just 1/2 dr by dt square. Kinetic energy per unit mass. Okay. And potential energy also I know how to calculate. It will be some number of order unity times gm by r. Right. So for a perfectly homogeneous solid sphere, it will be some 3/5 gm by r or something like this. The gravitational potential energy of a spherical system. So I have to plug those things in, and I have to remember that total energy is being conserved. So kinetic energy plus potential energy of the system is a constant. It is a constant determined by what? It is determined by the mass enclosed inside here, and it is determined by what initial kick I gave to the system. That was up to me. Right? So that fixed the total energy of the system. So both of these, when I put together, I find a very nice condition that the value of the radius when the virial condition is satisfied by this system is simply 1/2 of the maximum value of this radius. It's a beautiful calculation. It is there in all these textbooks. You can look at it. And this 1/2 comes out very, very naturally. Okay, there is no approximation involved. It's an exact answer. So this is called the virial radius of this system. And you can ask the question, what is the value of the density that is enclosed inside this shell at this particular time? And that turns out to be this particular number, 18 times pi squared. Again, an exact calculation. And 18 times pi squared is about 178. So this model is extremely nice because it is now telling you that although we didn't assume anything dramatic, this system is going to start from pretty realistic initial conditions, a tiny perturbation around the mean density with outward velocity flow as in Hubble's law. It will go outwards, it will turn around, it will come back in, and then if you demand that the real system should virialize, you can ask for not only the size of the system, but also the density of the system. Okay, so this capital delta is just the value of rho by rho bar, just a different notation for rho by rho bar, evaluated at the time where you are interested, at this virial time. And this value, rho by rho bar, is about 200, okay, 178. So 180, 200 approximately within 10%. So it is telling you that objects will form, virialized, equilibrated objects will form with a density contrast relative to the mean density of the universe, which is of the order of 200. Okay. And in fact, if you go back to the first slide and you see where these large structures are forming and what is the density contrast that you see there, they are numbers of the order of a few hundred. Okay, so this is not a very unrealistic answer that you have. In fact, it is so useful that when you run an n-body simulation and you want to identify in the simulation I will tell you in a little bit, it is just tracking the motion of fluid elements, okay, tiny fluid elements. But now I want to say that a virialized object has formed. Such objects are called halos in the jargon. A halo of dark matter has formed, which is virialized, gravitationally self-bound and everything. So now in the simulation, when I want to identify halos, in fact, I use this criteria. So I say that where is there a density enhancement in the simulation? I will go and sit on those peaks, and then I will grow spheres around those peaks, and I will ask the question at which radius of the sphere at that particular epoch do I get a density enclosed which is 200 times the mean density of the simulation box, and I will call that the boundary of the halo. Okay, so this is actually used in simulations in this way. Let's not worry about this thing. Okay, this is just a way of using this spherical collapse model as an interesting clock to other things, but I will skip this. Okay, so this is a spherical model, but the spherical model is not very realistic because actual inhomogeneities we have seen from the Planck map of the CMB sky that they are random. So we also want to understand now how randomly generated initial conditions would behave in a simplified sense. So the answer to this was proposed very long ago by Zeldovich. He was a Russian genius. He was working on many different topics in cosmology and in particle physics. So he has many contributions to important contributions to the field from these times. Okay, so this particular one is called the Zeldovich approximation. It is named after him and it is used even today in many different settings. So let's discuss what is this. It's extremely simple. So it says, let's assume that initial fluid element, wherever it is, it gets some velocity because of the initial condition. So we said that inflation generates a Gaussian random field. This creates, it does some quantum stuff. Then that quantum stuff gets translated into the curvature perturbation of the universe. Then the curvature perturbation couples through gravity to all the densities and velocities of the fluids that are inhabiting the universe. Okay, so I have a curvature which is fluctuating, and these fluctuations get imprinted onto the density structure and the velocity structure of all the fluids, in particular of dark matter. So now what Zeldovich said is that let's assume that this density field of dark matter has the field of dark matter has some density fluctuations and velocity fluctuations set up at the initial time. So now let's follow a particular fluid parcel in this field of dark matter. That particular fluid parcel has some mass and it has a velocity and it has a position. Okay, and you say that I will only look at equal mass fluid parcels. So that is allowed for you to do. So they will be distributed in space in different ways, and they will each have randomly chosen velocity vectors. And these velocities and their locations should be related to each other because they should overall define a Gaussian random field which ultimately came from the curvature perturbations and it obeys the equations of that. Okay, so these initial conditions have been given to you. They are self-consistent initial conditions. Zeldovich said, take any fluid parcel and ask what is its initial velocity vector. Okay, so let's say it has a magnitude which is this much, some x kilometers per second or whatever, some number of kilometers per second, v, and a direction which is pointing this way. In the real universe, you would expect that once this fluid parcel starts moving, it will start being affected by other fluid parcels, so maybe its velocity direction will change. Maybe here there is a huge density enhancement, so this fluid parcel which was initially going this way will start turning and coming closer to this. Okay, that's a realistic situation. Zeldovich said, forget about all this. You know the initial velocity, which you know how to generate with the Gaussian random field. You keep the direction of the velocity fixed always. Okay, so for that fluid parcel, the direction is fixed. For some other fluid parcel in the initial conditions, the direction may have been randomly in some other direction. Keep that one fixed also. Okay, so all of these fluid parcels will just move in straight lines always. But what will the velocity magnitude be for each fluid parcel? So there he said, don't do crazy things. You do realistic things. You go to linear theory. Okay, what we were discussing yesterday. So in linear theory, I solve ordinary differential equations, and I can solve the differential equation for the magnitude of the velocity for any initial condition. So you say that given that solution gives you magnitude of velocity as a function of time. Okay, and we know what that function of time is. It's some f of t. This is given to me by linear theory solution. So his model for the evolution of the dark matter field was the following. You take individual fluid parcels, and what do I need to know about an evolving dark matter density field? If I give you an initial collection of fluid parcels, I just have to tell you where those fluid parcels went at a later time. Once I know this, then I can go to that later time, paint all the fluid parcels at the correct locations, and then I can put a grid and find out the density field of those fluid parcels, right? So if two fluid parcels came very close to each other, initially they may have defined a density field which was very small fluctuations, but later if they come very close to each other, the local density there can become very large. Okay, so it will do something. So I can always define the density field like this. So his model was this: you take all fluid parcels, their positions and velocities at the initial conditions are known to you. You move them by defining their velocity vectors to be along fixed directions given by the initial directions, and their velocity magnitudes to change according to a function of time which is determined by the linear theory solution that we know how to calculate. Okay? The result of this is shown in the simulation here. So this was done by a former PhD student of mine as a as a graduate school project. And you can see here that what she's showing you is that, okay, she's also zooming out a little bit because she wanted to be aesthetically pleasing and so on. But notice what is happening to the structure that you start with. Okay, so let it loop again. So when it loops, you will see that it starts with a very smooth looking distribution. See here, there is almost no structure. It's completely smooth. And then structure starts to form. All right. And what kind of structure is forming? It looks exactly like the cosmic web that we have been discussing all along in data and in the full simulation that I was showing you initially. Okay, so it's remarkable that already this simplistic model produces a pattern which is not very different from the patterns that we see. So that tells you that the pattern there is actually just, its origins are very simple. It is just a Gaussian random field in which you have to move particles according to linear theory. Okay, so linear theory is the critical, so there are two critical ingredients here. One is the Gaussian random field, and the other is linear theory velocities. Okay, this is already enough to produce the pattern. Now there are problems with this thing. Suppose you can say, why did I stop at a particular epoch? Why didn't I just let the simulation keep going? Well, you can imagine now what is going to happen, right? If I don't allow particles to change their directions of motion, they will eventually meet each other and then they will just keep going, right? So collection of particles will come, they will converge at some point, but then if I let the simulation to run, they will just keep going and they will keep going forever. So if I had kept this particular simulation running forever, you would again reach a situation which is perfectly homogeneous. Okay, you would randomize all these nice correlations that you see here. So that is not very nice, and that is happening because the Zeldovich approximation does not correctly account for gravity. The fully non-linear effects of gravity are not accounted for. Only the linearized effects of gravity are accounted for, right? Because linear theory goes into this calculation. But non-linear gravity will take two fluid elements that are doing this, and it will make them bend towards each other, and then maybe orbit around each other, right? And then they will become bound to each other, perhaps. So these things don't happen in the Zeldovich approximation, but it is nevertheless extremely useful. And in fact, it is used to set the initial conditions of all current n-body simulations which are solving the full. Okay, so it is an approximation, but incredibly useful, not only in the practical sense for setting initial conditions, but also qualitatively for helping us understand how the cosmic web emerges. So, having said all this, it is now worth realizing that the current state of the art does not use analytical approximations to do serious stuff. Okay, so when you want to do serious stuff, when you want to put in a lot of money into observing program and then say that I am doing this because at the end I will learn something about my universe, then you have to justify that amount of money also by doing very careful analyses of the data that comes out of such program. So in order to do these data analyses at the level where we trust the things that we are doing to, percent level accuracy, etc., you have to solve the full problem. The only way to solve the full problem is to do it numerically. And that is why numerical simulations have been developed over the last several decades. And by now they have reached a stage where they span a wide range of wide dynamic range in masses and in length scale. So here I've shown you couple of pictures, which are publicity pictures from these two simulations, MICE and Millennium. Millennium was one of the first really large high-resolution simulations. MICE is another one that came out about 10, 12 years ago. And today there is a large number. Okay, so in fact, this list is not even complete. There are now even more coming up. There's something called UCHU, UCHU. It's a Japanese word, and collaboration is a Japanese collaboration. They have currently what is the largest and highest resolution simulation available in the world for these kind of using this kind of thing. Then there are other classes of simulations. So in these simulations which I have listed here, they are only considering the effect of gravity. They are not considering the effect of any other kind of physics, like astrophysics. Okay, so they are not saying how do stars form, how does gas evolve. So they are not doing hydrodynamics. They are not doing star formation. They are only considering the effects of gravity. So these are gravity-only simulations. Sometimes they are also called dark matter-only simulations, because it is as if you are saying that my universe is comprised only of dark matter, which does not have any electromagnetic interactions, and it does not have any astrophysics and so on. It does not have any thermodynamics. So these dark matter only simulations or gravity only simulations are now very, very well developed. And this IUCAA is the last, like the latest one. There may be others in the future also. Okay, so in these simulations, what happens is you want to solve what is called the collisionless Boltzmann equation. If you remember a little bit of statistical mechanics, the Boltzmann equation tells you how a fluid system or how any system evolves in its phase space. Okay, so what is the number density of particles in phase space? Phase space is the collection of the spatial coordinates and the collection of velocity coordinates. So in any given phase space volume element, how many particles there are at any given. Okay, so and then the Boltzmann equation tells you how to approach this problem. And when you take moments of this Boltzmann equation, when you integrate the Boltzmann equation against velocity and multiply by powers of velocity and then integrate over velocity, you will get the fluid equation. Okay, so the continuity equation comes from integrating the Boltzmann equation just like that. The Euler equation comes from multiplying the Boltzmann equation with the velocity vector and then integrating over velocities and so on and so forth. Okay, so there's a well-defined approach to doing this. So the overall goal is to solve the collisionless Boltzmann equation, but with cold initial conditions. So initial conditions should be compatible with cold dark matter. So the initial conditions don't have any velocity dispersion. They only have a bulk velocity and a density. So these initial conditions, we want to solve this. This equation with these initial conditions cannot be solved analytically. It is impossible. Yeah, so it is not that we have not been able to figure it out. It cannot be done. It is a numerical problem. It is a 6 plus 1 dimensional problem with random initial conditions. Okay, so we don't know how to do it. In fact, it is incredibly difficult to do it numerically also. Nobody has managed to produce a convincing solution, a numerical solution of this, which solves the full 6 plus 1 dimensional problem. Okay, so what people do instead is to introduce an approximation here as well, and then test whether that approximation is accurate enough for our purposes or not. Okay? So the approximation is called the n-body technique, where you say that instead of solving for the distribution function in 6 plus 1 dimensions, I will say that let me statistically sample the distribution function at the initial epoch. So I will say that where the distribution function is supposed to be large, I will sample more particles. Where the distribution function is supposed to be a small value, I will sample less particles. So it's a statistical approach. And it says I have my initial distribution function, which my theory gave me. I will pretend that it is a probability distribution function and I will sample. Okay, so in high density regions, I will get more particles. In low density regions, I will get less particles. So it's like saying I've generated the initial density field of dark matter. And because I'm actually generating the initial distribution function, I not only get the density field, I also get the velocity. And the initial conditions are cold. So once I have density and velocity, I don't have to worry about velocity dispersion or temperature because my temperature is 0. Okay, so my initial conditions are well defined. Having set up these initial conditions as a sampling, I will simply ask the question, how do the sampled particles move according to my theory of gravity? Okay, so I can convert my fluid equations into a system of particle motion. So this is what is technically called going from the Eulerian picture, where Eulerian picture means I sit at a point and I ask what is the density of the fluid here, what is the velocity of the fluid here as it sloshes around me. From that picture, I move to the Lagrangian picture, where I say that give me a particular fluid element and tell me where it was in the initial conditions and what was its initial velocity. And I will follow its motion. I will sit on it and I will see where it goes. Okay. So that is the approach that is taken here. The Lagrangian approach. I start with an initial set of particles. They are not microscopic particles. They are particles which are simulation particles. They represent fluid elements. And I will follow these fluid elements as a function of time. I will determine what their equation of motion is. I will solve that equation of for every fluid element. Okay, so that is what is written here. So I sample the phase space distribution function with mass tracers, which I call particles. And I follow their positions and velocities using what? Basically just Newton's law. d2x by dt squared is gradient of the gravitational potential. What is that gravitational potential? In the spherical approximation, that gravitational potential was just gm by r. And its gradient was gm by r squared, minus gm by r squared. Now it's more complicated. So the gravitational potential is not just determined by a spherical distribution. It is determined by whatever all the other particles are doing at that point of time. Okay. So given the initial conditions, I can ask at a given point, what is the gravitational potential gradient at that point? That tells me the acceleration of this particle. I have to do that at all particles, okay, at all locations. So for every particle at the initial time, I can calculate the acceleration. Once I have an acceleration and I have a time step, I can multiply the acceleration with the time step and I can get the increment in velocity. Correct? So now I have the velocity of the particle at the next step, and I already had the velocity of the particle at the previous step, so I know its position increment also. So I know now where the particle has moved and what is its new velocity. Okay. Now I know where all the particles have moved to. Every particle moved to some slightly different point. I look at this collection of new particles at time 0 plus delta. I calculate the gravitational potential at every place. I calculate its gradient. So now again, for every particle, I have an updated version of its acceleration. And basically, I evolve this. Okay. And now there is a numerical techniques problem of how to do this efficiently and how to do it with least amount of numerical error being accrued. So these are algorithms that people have developed over the years, and these are used. Good. So all of this is done, and the Poisson equation tells you the gravitational potential. You have to be a little bit careful because you are not solving the equation of ping pong balls which are going to collide with each other and bounce off. So you are actually trying to solve for the evolution of fluid elements which are collisionless, because if they were collisional then they would be interacting with baryons and photons and you would see them. But you said this is dark matter, so it does not have any interactions with other stuff and with itself also. So these fluid elements, when they come close to each other, they should not be, they should not start heating each other up and things like this. And they should not collide off, they should bounce off of each other. They should pass through each other because they are collisionless. Okay, how they pass through each other now becomes a problem of detail. As in, you have to decide, because you have approximated the system. If you were solving the full Boltzmann equation, you would not have this problem. It would take care of itself. You have now approximated the system. So you have to worry about what happens when two fluid elements come close to each other. Whatever you do here will be wrong. Okay, because there is no correct theory of doing it, because you have approximated the correct theory. So you say, okay, I will live with this approximation. I know that what I'm doing is wrong, but I also know that this mistake happens only when things come close to each other. So only when separations become very small. So when I analyze my simulation, I will simply ignore whatever happens below some minimum separation. If the density structure below some minimum separation is doing something very interesting, I will say it's okay, it may be interesting, but I don't trust that I have done it correctly. Okay, so I have a minimum resolution. The resolution of the simulation is decided by these kind of arguments. Okay, and then you can do other things. For example, you don't want to brute force solve the positions of all these n particles, because n in the n body technique can be these days, typically here, for example, is 1 billion. Okay, so you solve typically, if you want a good simulation these days, which you can run on the IUCAA HPC, you put in 1 billion particles. Below that number, you start to get effects due to having, discretization and not enough particles, noise due to not enough particles. So 1 billion particles, if you want to make them interact with each other, this is an n squared problem, and it is not an efficient way of solving the system. So there are techniques that are developed using Fourier space, Fourier techniques, tree-based techniques, etc., which can help with efficiency of the code. Okay. Having done all of this, okay, I have developed a code now which solves this system. It is approximate. I did all my various, I ran everything and I created a density. How do I trust anything that comes out of the density field here? So I have to do a further test. So I have to say, suppose I had doubled the number of particles. Okay, what would I get? Suppose I had decreased the volume of the simulation. What would I get? So I have to do all of these studies to check whether the final statistics that I get out of the simulation have converged or not. And if they have converged, then I'm happy and I say this is a prediction of my theory. Okay, so this is the state of the art for how theoretical predictions are now made using the n-body. So some of the statistics that one constructs out of these simulations I have just listed here. So for example, what I mentioned earlier is that once you have the density field, and the velocity field of your dark matter in the simulation box, you can go around and ask where is the density field a peak, and then at that peak I can put a sphere and I can ask questions like are the particles inside the sphere gravitationally self-bound or not? Meaning, is there a total energy negative? Okay. Then I can ask the question, has that set of self-bound particles virialized? Yeah, and then I can ask, when two such balls or halos meet each other, what happens to them? Do they retain their individual identities? Do they merge into a single system? What happens? These kind of things people ask, and you can then come up with ways of identifying these halos. You can say that I have a big halo and a small halo fell inside it, but I can still see that there is a small halo. So this small halo is called a sub-halo of the big halo, and this is called a substructure. Okay. Then I can ask questions like, which sub-halo came from which halo in the past? So which halo merged with me to become a big object? So this merger hierarchy you can develop, and you can calculate as a function of time. You can construct what's called a merger tree, where you say that for a given halo today, I can ask which are all the halos at some earlier time which came and became the halo today. Okay, why is this interesting? Because we think that galaxies form in these halos. Okay, and the kind of galaxies that form in a particular kind of halo depends on the nature of that halo. It doesn't just depend on how big the halo is. It also depends on how the halo got all its mass. It depends on the accretion history of the halo. So for this purpose, these kind of calculations are very important because they allow you to decide how many such halos exist, let's say with lots of subhalos in them, how many halos exist with very few subhalos in them, how many subhalos exist in a given kind of halo, okay, and things like this. So some of the examples are given here. So this shows you, for example, the number density of halos as a function of their mass. Okay, so what you can see is that actually this is probably showing you the mass density inside these halos. So it is showing you that there is a characteristic mass at any given redshift. I think these are different redshifts. So this is a low redshift. This is a low redshift. This is a high redshift. This is late times. This is early times. And what you can see is that the characteristic mass is somewhere around here at this early time, and it increases as you go to later times. So it is telling you that the typical halo in the universe is increasing its mass as a function of time, which is kind of reasonable. In the spherical approach also, you will see that a halo will increase its mass. You can do more than this. What is shown here is the profile of these halos. Okay, what is the profile? If I sit on a halo, this halo has a size, which is the variable radius. So I start from the center of the halo and I ask what is the density at the center of the halo. And then as I go outwards, how does the density change as a function of the radius away from the halo? So this is called the density profile, and that is shown here. And you can see is that at the center of the halo, or close to the center, the density is very high. And as it goes outwards, it becomes lower and lower. Interestingly, the way in which this happens seems to be a universal function. Okay, so this is what people realized in the mid-90s, and it has been confirmed very robustly in simulations now, is that for a wide class of halos, for any halo that you determine, that you identify in your simulation, if you ask this question, I sit at its center and I calculate the density as a function of distance away from the center. This function, as a function of distance from the center, is the same function for all these halos. It only depends on two quantities. It depends on the total mass of the halo. And for more massive halos, of course, the density will be larger. For less massive halos, the central density will be smaller, and so on. And it depends on one other parameter, which basically decides where this density goes from being very shallow to very steep. Okay, so you can see that here the density change is very shallow. Here it has become steeper. So it has gone like this, and then it has become steep. So where does this transition happen? That is called a scale radius of the halo. So this is the other parameter which this function depends on. But this function only depends on these two parameters. If you take any given halo and tell me what are the values of these two parameters, I can tell you the entire functional form of this density profile. Why has this emerged? Okay, why has a universal density profile emerged in simulations? Nobody really knows. It's an open question. Okay, there are some answers. There are some attempts to answer this question, but nobody has a convincing argument which says that I can derive this density profile from first principles. It is a emergent phenomenon in the late time universe that we have seen because we now know how to run inverts. And then there are other things that you can do. For example, the power spectrum that I was talking about earlier, that was the power spectrum in linear theory. Now you can calculate the same power spectrum at the end of your simulation. Right? Now this is the most realistic answer that you can get. You can ask how does this power spectrum in the non-linearly evolved simulation compare with the prediction that I would have obtained from linear theory at the same epoch. And that is shown here. So a ratio of by some reference model, and what you can see is that the linear theory prediction is this particular oscillating thing, the dotted line, and the simulated power spectrum is shown by the data points. And you can see that the data points are substantially higher than the dotted by factors of 20-30% at these scales. And if you look at these wave numbers, these are not very small scales. This wave number, if I just take 1 over k to convert into a wavelength, this 1 over 0.1 is like 10. So these are 10 MPC, and then there's a 2 pi also. So these are like 30 MPC scales. So they are relatively large scales, and already here you can see several tens of percent effect of these nonlinearities. If you extend this to even smaller scales, even larger values of k, you will see orders of magnitude. Okay, so that is simply not captured by units. So you can see that these are now important effects, and currently data that are coming from large volume surveys. The reason this plot is shown by these people is because this is an interesting regime where constraints from data can be accessible very soon. It's already an old plot. And you can see here that, okay, so I have not shown that the expected error bars from data, but the expected error bars there are supposed to be few percent. Okay, and these effects are tens of percent. So if you don't model these effects, if you say, I will trust linear theory, then I will try to use this dotted line to fit my data. Okay, but the dotted line was constructed using some parameters in your model. Omega matter is something, omega lambda is something, okay, Hubble constant is something. I use the prediction from linear theory to tell what the data should look like. The data may be somewhere here. Okay. And if I use linear theory to predict the data, I will make a huge mistake. Because my linear theory will say I cannot explain the data with the omega matter that CMB tells me. I have to change omega matter. Okay, or I have to introduce a dark energy or something like this. And then I will be able to explain the thing. But that is simply because the linear theory is making the wrong prediction. The correct prediction is this one in the nonlinear theory. So I should be comparing this one to the data. And then when I do that comparison, maybe I will find that I don't need anything extra. Okay. So this is the situation we are in right now. That all the comparisons of these simulations to data are telling us that our base model of lambda CDM, omega matter roughly 0.3, omega lambda roughly 0.7, gives a pretty good description of all the data that we have access. So this is what I wanted to say about simulations. That's it. Now there is an option. Okay, so there was one question from yesterday which I will answer soon. But apart from that, there is an option. You guys decide what you want to do. I could stop here because it's a good point to stop and it gives you an overview of the field. Or I can take up one more topic, but then that is one more topic. It will take like 15-20 minutes to discuss. My personal opinion is that one should stop here, and if you are interested in more details, I will just list out the topics that I could have talked about. And if anybody is particularly interested in knowing more, you can approach me later. Okay, so you are here for another week or whatever. I am also here next week. So you can approach me personally later, or you can come in a group or whatever. So maybe that is a good thing to do instead of starting a new topic. Okay, so before we proceed, let me answer one question from yesterday. There was this question. It was in this one or in this one? Go to that slide. Or maybe I was. No, it is here. So there was a question related to this discussion. So what I was saying was that during radiation domination, the gravitational potential decays. Okay, and as soon as the wavelength enters the Hubble radius, the gravitational potential corresponding to that wavelength decays, while a longer wavelength will stay outside the Hubble radius for a longer time. It will enter during matter domination, and after that it will be more or less constant. And the constant we had discussed here afterwards, right? That if the gravitational potential is a constant, it implies that the density contrast will grow at those wavelengths because there's a power of A that appears when you account for all the co-moving and all the time dependence. Good. So that part is okay. The question was, why does this decay happen? And can you think of it as a diffusion of something? So it is a little bit more subtle than that. So what is happening here, you have to remember, is that you ask yourself, what are the different kinds of energy components in the universe and where are the fluctuations? So the energy components are in relativistic matter, which is photons typically, and non-relativistic matter, which is dark matter. And for this discussion, you can ignore the fact that there are also baryons which are coupled to the photons and then later become decoupled and non-relativistic. Let's say there is a universe in which there are photons and there is dark matter, and they don't talk to each other. At this epoch, at these early epochs, what are the fluctuations and what is the density field? So now the density field is dominated by radiation. Okay, the fluctuations have fluctuations in the gravitational potential, the fluctuations in the dark matter density and velocity, and the fluctuations in the temperature of the photon field. These are the fluctuations that one has to think about. Because the universe is dominated by radiation, the gravitational potential will mostly respond to the fluctuations in the radiation field. Because the relativistic Poisson equation is Laplacian phi plus some derivatives of phi equal to what? All the density fluctuations that are there. The density fluctuations are mean density times density contrast. Okay. So even if you assume that all the density contrasts are comparable to each other, the mean densities are not comparable to each other. The mean density of radiation is much, much more than the mean density of non-relativistic matter. So the fluctuations of radiation are more important than the fluctuations of non-relativistic matter at these epochs. So you have to, in order to figure out what is the evolution of the gravitational potential, you have to throw away the terms involving the dark matter fluctuations and only consider the radiation fluctuation. Good. So the system we are effectively talking about is a inhomogeneous radiation field interacting with gravity. Radiation perturbations have a lot of pressure, okay, because the radiation field has a lot of pressure. What does pressure do to the evolution of fluctuations? So if you think about a simple harmonic oscillator kind of problem, where I have a harmonic oscillator with an inward attractive potential, if I add a pressure term, that pressure term will tend to push in the other way because my sound waves go outwards. Okay, so it's not diffusion really. It's just sound waves. So bulk motion of the sound waves will try to keep my fluctuations from growing. The density fluctuations will not be able to grow in the radiation. If you ask now what happens to the corresponding potential fluctuations, the heuristic argument is the same as we gave before. If the density fluctuations are not growing, then the potential fluctuation must decay. Right? Even simple Poisson equation will tell you. So roughly speaking, that is what is happening. The radiation pressure is preventing the fluctuations of radiation to grow in size because it is a relativistic fluid, and that makes the gravitational fluctuations decay. Okay. Once the gravitational potential fluctuations decay, you can ask the question, what happens to the growth of the dark matter fluctuations? And then again, the same argument will tell you that because the gravitational potential is decaying, the dark matter fluctuations cannot really grow. Okay, so they grow, but not as much as they grow later. So that is a matter of belief. So I hope that clarifies. Okay, good. Now just let me wrap up by saying a few words about how you can use large-scale structure to do cosmology. Okay, so I will just flash the starting slides of these talks. This one is here, and this one is here. So one of the ways that you can do cosmology with large-scale structure is the so-called baryon acoustic oscillations. Okay, so in this, what one argues is that, remember I said that there is a sound horizon in the universe up to the time of last scattering, how much a density wave would have gone. And I already argued this in the beginning that whatever happens to the photons eventually will leave imprints in the ordinary stuff also, in the hydrogen gas as well. And because the sound wave has taken both photons and hydrogen gas as a density enhancement out to some radius, 150 megaparsec, right? And then the hydrogen gas, after the photons have free stream, the hydrogen gas does not have any radiation pressure anymore. Okay, so now it only feels the effect of gravity. Effect of gravity is attractive, so this hydrogen gas will start condensing. And then you have to ask what happens to hydrogen when it condenses. Okay, so there is a long series of things that may happen because it will condense, it will become hotter. Then once it becomes hot, if there is molecular hydrogen, then there will be some line transitions that can get excited. So what are line transitions? There are electrons that are moving between states, quantum states, releasing photons. So once these photons are released, if they go away from the system, they have carried away energy. No, all photons have energy. So this hot system, once it starts radiating these photons, it will become colder. But a cold system is allowed to contract further. Okay, so if I have sufficiently efficient radiation, then my system, although it will heat up as it condenses, it will radiate away energy and it will cool further, so it can condense further. Okay, and in this process, if it is efficient enough, then eventually you will reach a situation where there are tiny clumps of gas that are forming. Then there is a further theory of what happens to these clumps, turbulence, etc. Effects may come in and so on. Magnetic fields may play a role. And eventually, these clumps will start forming protostars. And they will organize themselves into galactic disks and so on because of angular momentum. So this is how galaxy formation will proceed. But where is all this occurring? It is not occurring, once the sound wave has reached a certain radius. It is basically all this galaxy formation is occurring there. Because those hydrogen clumps are not now going to start moving around with relativistic velocities. They are just going to gravitate locally. Okay. So if I have generated an enhancement of hydrogen at 380,000 years after the Big Bang, that enhancement will roughly maintain its enhancement structure, even if galaxies form. So if I look at the distribution of galaxies that have formed and I look at them at a later epoch, this imprint of 150 megaparsec will be there. Because when I look at galaxies here, chances are that 150 times 2 megaparsecs away, I will see an enhancement of galaxies. Okay. So this imprint is there, and this is called baryonic acoustic oscillations. Do I have a slide which just shows the effect? Okay, so this is the cartoon picture of what I was talking about. And then this is the actual detection in 2005. Okay, so what one is counting is how many galaxies there are, which are separated by some separation. And what you see is that around 100 or so MPC, there is a little bit of a bump. Okay, so this bump was very, very, very exciting for all of cosmology because it was a direct prediction of your standard model. CMB had already seen its fluctuations, right? WMAP was already around at this time, and there was a prediction that you should see a bump. Okay, a skeptic would say that if I erase the theoretical lines, the bump in the data is maybe not very significant. It may even be random. So that situation has changed now. Now here is a more recent 10 years ago is this situation. There are no theory lines in it. Okay, there is only the data. There is a clear enhancement of the number density of that. Okay, so this is the way now, this is the situation now. It has become even better now. This is BOSS data release 9, 10, 11. Now we are in data release 12 and then even subsequent ones, data release 15 and so on. Error bars have shrunk considerably simply because you have seen more and more galaxies. Okay, so using this, you can now start asking questions like, what is my theory prediction that goes through these data points? What are the parameters on which it depends? And I have my data now. So I can do a statistical analysis, compare all my theoretical models with this data set and ask what constraints are. Okay, so this is one game that we do. This is at very large scales because this feature is at 100 or so megaparsecs. So in order to get this feature right, you need immensely large volumes. You need volumes that are at least 10 to 100 times, 10 to 50 times larger than this number. Okay, along one linear dimension. So this is 100 MPC separation. See, in 3 dimensions, it is 150 cube volume, which is just determined by this feature. To statistically get this feature with sufficiently low noise, you need volumes that are at least 10 to 50 times larger than 100 MPC cube. Okay. So you can ask what is the size of the survey that you need in order to get this. So this is a very large scale feature. There is another feature that happens at small scales, and these are called redshift space distortions. Physics idea here is very nice and simple. It goes back to Zeldovich almost. What one says is that all our observations of 3-dimensional positions involve what? 2 dimensions come from angle in the sky, right? The third dimension, which is distance, where does it come from? Can someone tell me? How do I tell the distance of an object that is cosmologically far away from? From the redshift. Excellent. Okay, so and then suppose these are not that far away from me, they are at redshift of 0.1 or so. Hubble's law is what I will use to infer distance from redshift. But now that was in the homogeneous and isotropic universe. In the inhomogeneous universe, we know that all fluid elements have local velocities also, and these velocities are random. So these galaxies also, if you think of them as tracers of the underlying density field, they also have local random velocities. But I also know from standard Doppler physics, undergraduate Doppler physics, that if a particle is moving towards me, it will create a Doppler redshift. If a particle is moving away from me, it will create a Doppler blue shift. So this small amount of local Doppler redshift or blue shift will add to the overall cosmological redshift due to Hubble expansion. Okay. So that redshift came because the universe is expanding. This one is coming because if I go to the location of a fundamental observer there, a fictitious fundamental observer, and I ask, how is the galaxy moving? That galaxy is moving with 10 meters per second local random motion. But that motion will add to the redshift that I am measuring today. Okay. So the cartoon picture is here that the redshift that I observe is determined by the Hubble flow due to a homogeneous and isotropic universe, plus a contribution due to the peculiar velocity, but only along the line of sight, right? Because I'm looking there, and the redshift is a spectrum that I take from there. So only the line of sight peculiar motion will create a Doppler. Okay, so this is the observed redshift. But now, when I observe it, this is only one number that I have, right? So I don't know what contribution came from Hubble expansion and what contribution came from peculiar motion. So I will just use this redshift and I will apply Hubble's law. So I will take Cz by h and I will call that the distance. So that is called there's a name given to that. That is the redshift space distance or redshift space position of this galaxy. That is denoted by S. This is the actual co-moving position of that object. And this is the extra piece that came in because there is a line of sight peculiar motion. Okay, and here I have written everything in terms of vectors. The reason to do it in terms of vectors is that now you can see that if I have many such galaxies at different places, I am only able to observationally determine the S values for each of them. Okay, there are 3-dimensional vectors. So when I calculate a 2-point correlation function as a function of separation, the separation that I calculate will be differences of S values. For one galaxy, I'll have one S value. For another galaxy, I'll have another S value. I'll take the vector difference between them and I'll calculate a separation. But that separation is not the co-moving separation of those galaxies. The co-moving separation would be the difference of the X values. Okay. So on top of the co-moving separation now, I have an additional effect, which is the difference between these two velocities. And this difference is a difference of the velocity of one particle and the velocity of the other particle projected along the line of sight. So the pairwise velocity difference affects my calculation of physical separation. Okay. So now you may say this is a problem because what do I do? Because now I can never calculate separations. I can never predict what my theoretical model, how it should be compared with the data. It's not like that. It is actually interesting because if you see what happens here, this is not a very clear picture. Let me see if there's a clearer picture. Okay, so this is a better cartoon to understand what is happening. So imagine a large scale overdensity. Okay, so at like a spherical overdensity of let's say 50 MPC radius or something. We know from linear theory that an overdense region will create a converging flow towards me. I will attract mass in this overdensity region. So imagine this large scale overdensity which we are viewing. So this whole overdensity is placed far away from us. But this overdensity, because it is an overdense spherical region, it is contracting into itself by some amount. So this is the picture, the physical picture, where the actual positions of these tracers are in this circle. And because this is an overdense region, the velocities are all pointing inwards towards the center of that region sitting there. I am now looking at the object from this side. Okay, my line of sight is this way. What will I infer? For this object, I will see the effect of an infalling motion. So the actual cosmic redshift, I will take that and I will subtract something from it because this infalling motion will be a blue shift. So I will subtract some distance. So my inferred distance will be slightly less than the cosmic distance. Correct? For this one, opposite thing will happen. My inferred distance will be slightly larger because this guy has a velocity which is moving further away from me relative to Hubble's. So when I convert this this whole thing after observations into a map of these tracers, what will it look like? It will look like this, right? So this object will be slightly closer than it should have been, slightly further. These two objects will not be affected. They will be given their correct distances because there is no line of sight component to the velocity. So a circular looking object will become squished along the line of sight. Right? Good. And similarly, in an underdense region, a circular looking object will get enhanced along the line of sight. This is what happens with coherent flow. And this coherent flow is very nice for cosmology. Because this coherent flow, if I'm telling you that it is happening at 50 MPC scales, separation scales, these are linear theory scales, 50 MPC, 100 MPC. At these separations, my nonlinear effects have not kicked in. So I can use predictions of linear theory to say how much this squishing should happen. And then I can unsquish by that amount because I observe this, right? And my linear theory tells me that I should account for a squishing which is due to peculiar motions by some amount. If I fix omega matter to something, Hubble constant to something, the amount of squishing is predicted for. Okay. So now I observe an actual squish thing. I can ask the question, in order to unsquish this and make it into a circle, what are the cosmological parameters that I need in linear theory? Right? Because for any given set of cosmological parameters, I can make a prediction for the squishing and therefore for also the unsquish. So given a squished configuration, how much should I unsquish? And that depends on the values of the parameters. So if my data tells me how much I have squished, I can infer which parameters should be used so that the original thing is unsquished. I have determined my cosmological parameters. Okay. So I can do cosmology with this effect. This effect is called a distortion due to redshift space. So it's redshift space distortion, RS. Okay. So I will not discuss more of this. Visually, very interesting thing happens here because when I have a cluster of galaxies, the particles inside them, the galaxies inside them, don't have these coherent motions. They are not all infalling, they are not all expanding. They have random motions. Okay, and random motions you can show. Basically, what will happen is once in a while, a particle all the way at this side will have a very large line of sight motion in the opposite direction, just randomly. Correspondingly, something that is sitting here, it may have a very large line of sight motion either here or anywhere. So what this does is it basically creates a large distortion directly along the line of sight. This is called the finger of God because it was first seen in these relatively low volume surveys. Let me show you here. Okay, so this is one of the older surveys. It's good to see this because the finger of God effect is very apparent. Okay, look at this streak here. Look at this streak here, right? It is not that the galaxies are arranged in a line. This is completely unrealistic. What has happened here is that actually there is a large cluster of galaxies somewhere here in the middle. There is a large cluster of galaxies somewhere here. And these galaxies have random motions in them. So the random motions, when you convert them into distances, they have created these elongated features. So these were seen in these surveys. It looks like God has pointed finger. Okay, so fingers of God. And that is what is seen here. This also has interesting effects. The relevance of cosmology is a bit less, but it is still interesting. And if you really want to do cosmology, you have to understand how to model these fingers of God. Okay, so RSV and FOG, these acronyms you will see if you go into the literature. That is what I want to say about redshift phase distortions. And the last thing, in 5 minutes, I will not go into the rest of the slides here. I will just show you this nice image from Hubble Space Telescope. You may have seen this image in some of your earlier talks also. This is the Bell cluster, and these are super nice lensing rings here, right? And basically, this is a large cluster of objects. So the formation of these clusters is also an interesting question to ask. How do these large clusters come to be? Okay, and the number of these clusters, how many clusters you see of a given size in a given survey volume, this depends on what your cosmological parameter. In a cosmology where omega matter is very large, I will have more mass compared to a cosmology in which omega matter is very small. Okay, so because the universe has more dark matter when omega matter is large. So a universe which has more dark matter is more dense in dark matter, so it is more capable of forming large halos. Okay. So the number of large halos that is predicted at late times depends on what the cosmological parameters. So now I can do a survey in which I identify clusters that look like this. I say that, okay, I see based on the velocities and the positions that this set of galaxies appears to be gravitationally self-bound. And I count all these objects as a function of their mass, and I compare it to predictions of different cosmological models. And I can use that to do cosmology. Okay, so this is the way that one uses structure formation and the presence of large scale structure to make cosmological inference. So this is a big game, it's a big industry these days. And again, if you're interested, you can ask me questions. Okay, so I will stop here. That is the end of my lecture series. Yeah.
I just said that halos do not interact, or dark matter do not interact. So how can I identify what are the categories of halos without interaction? How can we identify?
No, they don't interact through non-gravitational physics. That's what I'm saying. I should also be careful. It's not that they don't interact. It depends on what dark matter is. Okay, we don't know what dark matter is. In the simplest models of dark matter, the interactions of that dark matter species as a particle physics species with other standard model species is very, very negligible. Okay, so and that is what is needed in order to explain observations. So that is the way in which they don't interact. But of course, they have mass. These particles have mass, so they gravitate. So you saw in the previous lecture that there was this simulation in which density was increasing in some places, decreasing in some places. So all of that is done with collision-less dynamics. But gravity is of course there. Gravity is the main thing. So then once that is done, then you can say, okay, how many halos of a given mass have formed? What is the density profile of these halos? What is the velocity structure of these halos? How many subhalos does a halo have? All these questions you can then ask. Yeah. No, you.
Sir, you said that the density profile of each halo almost becomes the same. So if we think of like two halos nearby, then can we like arrive at a contradiction that we have two different density profiles or something?
No. So when I say it is the same, it is the same family of functions. There is one family of functions which describes all density profiles, and that family of functions is defined by two parameters. Okay, so that is what has been seen. Now, what is the question about two different halos? So in general, if I have a big halo and a small halo, the density profile will be different because the big halo has its big density profile, small halo and smaller density profile. But the shape of that density profile, if I appropriately account for the effect of mass and of this thing which is called the scale radius, then those density profiles appropriately rescaled will look very similar to each other. That is what one is saying. What is the contradiction?
To arrive at it, like they might have points of intersection if it's possible.
Oh, that
then,
I see. Okay. So this is a question of the technical details of how halos are identified. What one typically calls a halo is one object which does not overlap with another. if an object overlaps with this object, it is difficult to tell them apart, and then it is difficult to characterize the density profile. Absolutely. Then there is a problem. This typically happens if you happen to catch the two halos just at the time when they are about to merge. Okay, then of course there's a problem. So when one does these statistical studies, you usually keep away such systems. They are a very small fraction. See what is happening. There are halos that are forming. Usually a halo will grow by just accreting small clumps of mass. So the mass that it accretes is not a mass in another halo itself. Once in a while, rarely, but sufficiently frequently, but not like all the time. Two halos will come together and one of them will fall into the other. Okay. So this is called a merger event, a major merger event, where two equal mass or comparable mass objects came and became one. Now, even in such a situation, if I take a snapshot of the simulation at a random time, it is not guaranteed that I will catch them just when they are touching. So the amount of time in which I have to take that snapshot is a very small fraction of the overall time of the simulation. So it is quite rare that I will capture a pair of halos exactly at the time of touching of their radii. Right. So usually what will happen is that they are a little bit far apart, and maybe later on one of them has come a little bit inside. So such systems in which one of them has come a little bit inside, this will be classified as substructure. Because what you will say is that there is an overall object, it is isolated, there's nothing near it. But when I look inside it, I find another object which is also there. So then I will say that the smaller object inside is a subhalo of the bigger object. Right? So there is no ambiguity there. But you are right that when I characterize the density profiles, these effects will create some systematic changes. That is absolutely correct. And the clean answers that I'm showing you are based on selecting only those halos where I am not going through a merger at the current epoch, or I may have gone through a merger, but I should not have a lot of substructure inside me, like masses.
And also in the spherical approximation, how could we say the mass is constant at the boundary? Will there not be gravity?
So that is a feature of the symmetry of that problem. So if you set up that particular problem, you will actually have a situation where all the shells are moving in such a way that they never cross each other. Okay, so the inner shells are high density, the outer shells are mean density. All of them are given Hubble flow initially. Okay, and then in that situation, those shells will always maintain their order. So even after the inner shells, what will happen? They will all go out, then they will stop and they will turn around. But if the inner density is a constant, then this point of time at which the turnaround happens is the same for all the inner shells. This you can show. And because of this, and then the outer shells will never turn. They will just keep going. So this entire object will simply decouple from the rest of the expansion and it will start contracting. And after contraction also, they will maintain their order. You can prove this as well. Okay, so that's why the mass contained in that overdensity is always the mass contained in that overdensity. The way the mass can change is if shells will cross each other. Okay, so I can set up that situation. Suppose I have a very steep density profile initially. Then what will happen is that the turnaround radius of the or steep profile like this. Okay, so if I have a density profile, which is, so I was talking about a density profile which looked like this. Instead of that, suppose I have a density profile which looks like this. Okay. So in the middle, it is at mean density. Then it increases outwards up to some maximum value, and then it falls off to mean density. Suppose I take, let me even make it clear. Suppose it is like this, simple. If I forgot about the rest of the universe and I only looked at mean density here, what would you say with initial Hubble flow? What will happen to these shells as a function of time? They will keep expanding at the standard rate, at the same rate as these shells are Hubble flow. But now these shells are at higher density. So they are going to turn around at some point. Okay, so imagine this particular shell is going to go outside, it is going to turn around. After turn around, it will start coming back in. But in the meantime, what is happening to these shells? They are going on, right? So there will be a point of time when these shells going outward will meet these shells coming in, and there will be a crossing of shells. So at the time of the crossing, actually the density locally will be infinite. because the shells will go through each other. And after that point, the mass constancy will also go, because now inside this particular shell, the mass that I'm counting is not just the mass of all of these shells. One of these shells will also eventually contribute its mass. Okay. So the mass will no longer remain constant. So in such situation, you cannot do the analytical answer. You have to follow the system numerically. It is still easy to follow because it is a simple one-dimensional problem. Only radius is changing and time is evolving, but it is a numerical problem. So these kind of problems also people have studied. Anything else? Yeah.
So in the numerical situations, when the potential is calculated, are these retarded issues in that sense?
Good question. So, or more broadly, are there relativistic effects that one must account for in the numerical stage? This became a hot topic for a few years, about 10 years ago, and now things have settled down because people understood exactly what is happening. So there was this worry in simpler way than what you mentioned. The worry is that I have a box, a simulation box, which is, let's say, 1 gigaparsec on a side. It's a co-moving size. So at any time in the simulation box, the co-moving size is fixed. That is how I run the simulation. The physical size, of course, is smaller in the past. Okay. So if I go sufficiently far back in the past, if my co-moving size is large, and I go back in the past, I can always ask how big is my simulation size compared to the Hubble radius at any given moment. Hubble radius today is of the order of 3 gigaparsec. Okay. So, and in the past it was smaller. So even a simulation which is 1 gigaparsec today, if I extrapolate it back in the past, it may reach a situation where its physical size is of the order of the Hubble size. Yeah? And in fact, even today, I can take simulations. I have means of running simulations which are 5 gigaparsec, which is larger than the Hubble radius. So what is happening? So then people say, okay, Hubble radius is not important, particle horizon is important. Okay, do that calculation. And with a 10 gigaparsec box today, extrapolated backwards, there will be an epoch when the size of the box, physical size of the box, is comparable. It may not be larger than, but it is comparable to the particle horizon. Okay. So now the worry is the following. I told you that the n-body technique assumes Newtonian gravity. The way you are moving your tracers is built out of Newtonian gravity. So how can you use Newtonian gravity when your simulation box is of the size of the particle horizon or of the size of the Hubble radius? You should surely be accounting for relativistic effects. The answer, after a lot of debate in the literature, 4 or 5 years of debate, turned out to be that you have to think more carefully about what happens on very long wavelengths in linear theory. Because at small scales, when I'm talking about particles that are separated by very small separations, even if the full simulation is 10 gigaparsec wide, if my particles are separated by 1 kiloparsec, Newtonian gravity is completely fine. Okay. So when particles are separated by small separations, I don't have to worry. I have to maybe only worry about what happens to particles that are separated by a large separation of the size of the simulation box itself. So really speaking, what you're asking is, if I do Newtonian gravity and I calculate the density field of my dark matter and I look at it at very long separations, am I solving the correct equations or not? This is really the question that one wants to answer. At long wavelengths, which are close to or larger than the Hubble radius, the equations of gravity should be Einstein's equations, not Newtonian. Einstein's equations have an interesting feature which PP may have told you about. They are invariant under arbitrary changes of coordinates. There's a general covariance in the problem. Okay. So the user is free to specify their choice of coordinates. When you do perturbation theory, you are not allowed to change coordinates arbitrarily, because you cannot say that my homogeneous and isotropic universe, I will convert t into x and x into t. Okay. You can do that if you're, Sankey or something. But then you will be in a situation where your time coordinate is behaving like space and one of the space coordinates is behaving like time. Typically, you don't want that. So in cosmology, what people say is that there is a special class of coordinates in which the universe is homogeneous and isotropic and the equations are very simple. Let us not go very far from these coordinates. Okay, so keep close to these coordinates. How far can you go? This is determined by how much of a fluctuation around the homogeneous universe you are allowed to tolerate. Okay. And in the initial conditions, we know what this is. It is 1 part in 10 to the 5. So the changes in coordinates that you are allowed to do are also 1 part in 10 to the 5, but there is this freedom. 4 arbitrary functions you can pick on your own. Nobody can stop you. And as long as the magnitude of these functions, t goes to t plus something, x goes to x plus something, y goes to y plus something, 4 such somethings you can define. As long as the magnitudes are very small compared to 1, of the order of the perturbations that you are allowed to count, right, of the order of 10 to the minus 5. This choice of such specific kinds of coordinates is called a gauge choice. Okay, so instead of a general covariance, there is something called diffeomorphism invariance. So under infinitesimal diffeomorphisms also, the theory is invariant. And this is the kind of thing you want to do. Now coming back to this problem of what happens to the equations of motion. Since the equations of motion themselves have this freedom, you can always say that I am choosing to do this particular enhancement of update of my particle positions and velocities. I ask the question, at long wavelengths, which gauge choice does this correspond to? I can answer this. Okay, I can work it out by saying, okay, given that I have moved by this much, given that the acceleration I calculated was this much, that means that the velocity has changed by this much, the density has changed by this much, and I can compare those densities and velocities to the density and velocity evolution in some standardized choice of gauge. Okay, so there are some conventional choices of gauge that are available in the literature. So I can say, how different is my choice of gauge compared to this choice of gauge? Even if I don't say it, all I have to say is that when I go to observables, how should I construct the observable quantity in the given choice of gauge? So in fact, now after this thing called settled, people just invented a name for this. They called it the n-body gauge. Okay, so the answer simply is that these are Newtonian, they are Newtonian-looking simulations. More strictly speaking, they are simulations performed in the n-body gauge. Finished. When the controversy was still raging, I had asked this question to someone, to a professor, and they gave me a very nice answer to this. So at the time, I was also quite bothered about this. How is it that we are not accounting for relativistic effects? The answer was, think about electromagnetism. So the way I had posed the question was, the Poisson equation is Laplacian phi equal to density. It's a local equation with no accounting for light propagation. So it's instantaneous speed of light, right? Instantaneous propagation of information. So how is this consistent with cosmology? So the answer was, think of electromagnetism in the Coulomb gauge, where you have an equivalent of the Poisson equation that you're solving there also. Do you ever worry that light is not propagating at the correct speed when you do electromagnetism in the Coulomb gauge? Have you ever worried? I said, no, I'm not worried. Then why are you worrying about this? Right? So that is the idea, that there's a gauge effect there. There's also a gauge effect. All right. Anything else?
Aseem, there is question online.
Yes, go ahead.
When the universe was small, all the regions could interact with each other, but as the universe expanded, not all the regions were in contact with each other and evolved independently. In such scenario, is such scenario possible? If yes, how much it contribute to the inhomogeneity of the universe?
Okay, so this I have discussed when I was talking about inflation, right? Because the way to do it is to go back to the lecture on inflation and follow the argument of the particle horizon. So talk to each other basically means being inside each other's particle horizon. And then depending on your model of cosmology, the particle horizon will behave in one way or the other. And what we have seen is that you need it to behave in a particular way. The co-moving Hubble radius has to decrease for a brief period of time, such that particles which were initially in contact with each other become causally disconnected for a brief amount of time. Okay, and then that is the way to generate initial conditions that are consistent with our universe. So I hope that sort of answers the question. Okay. All right. So if there's nothing else, we can stop. And thank you for your attention.
Thanks.